So just going to talk about, this is going to be a very introductory talk on what mathematical modeling is and how we're going to kind of focus it on financial applications. So just have kind of a definition of what modeling is. So basically you're putting a model together, and where it's being used in the world, putting a model together, and you've done this your whole life. I'd like to just go over maybe a very simple example. So the mathematical model of 1 plus 1 equals 2. So technically that can be considered a mathematical model. So we use this model when we're adding two units of something together. So it is implied in the model that the two things we're adding together are of the same type. So for example, you could use the mathematical model, 1 apple plus 1 apple. You could use the mathematical model 1 plus 1 equals 2 to perform a computation like 1 apple plus 1 apple equals 2 apples. So this would be a correct use of the model. If we then said 1 apple plus 1 orange equals 2 apples, well then we're using the mathematical model 1 plus 1 equals 2, but we're misusing it because it's implied that they're both of the same type. And these are, apples and oranges are different types. So we could have said 1 apple plus 1 orange equals 2 fruit, because they're both fruit, and as long as the type stays the same. But this would be an incorrect use of the model. Okay, so that's just a very simple idea of what a model is. And models that are discrete, let me just go back to that, models that are discrete, just adding two numbers together, probably not very interesting, and you probably just do those. You wouldn't even have to write out a model for how to do that. Where modeling starts to get interesting is when there's a random event involved. So for example, if we wanted to model what happens when you flip a coin twice. Well, let's say, for example, let's say you wanted to count how many times you'll get a heads by flipping a coin 2 times. So there's a random event. It's not a discrete thing. It's not like we just know it's going to land on heads or tails. We don't know. There's a random event occurring. So in our mathematical model, we could put we could say that we're going to let the letter F, which is, for the flip of a coin, we're going to let that represent the random event that occurs, the flip of the coin. And we're going to say that F has a 50% chance of flipping and becoming heads, and a 50% chance of flipping and becoming tails. So if we go to model, what are the number of heads we'll get on 2 flips? We'd have to say we're going to flip the coin and count up how many heads happen on the first flip. It's either going to be 0 or 1. And then we're going to flip the coin again and count up how many heads there are. So the model will be 2 times. We're going to do the event of flipping the coin and then counting up how many heads came up on that flip. We're going to do that event 2 times. So the number of heads is going to have a 25% chance of being 0. There'll be a 50% chance of being 1 head. That would be like the first coin is heads and the second one is tails, plus the first one being tails and the second one being heads. And then there's a probability that we'll get 2 heads, and that would be 25%. That would be both coins are heads. So that would be a way of modeling a random event. Okay, so let's go over maybe slightly more interesting one, would be the roll of a dice. And then maybe combinations of rolls of dice. So suppose you wanted to model a roll of a dice, and let's say the dice has 6 heads, 6 faces on it, 1, 2, 3, 4, 5, 6. Each one has a 1/6 chance of happening. So the probability distribution is a 1/6 chance the dice will come out of 1, 1/6 chance the dice will come out of 2, yada yada yada, and then a 1/6 chance the dice will come out of 6. So if we wanted to model, let's say, what would be our total score if we rolled the dice n times? Suppose, like for example, suppose we roll the dice 10 times. We said, well, what would our score be? Well, if the first roll is a 2, the next roll is a 6, well 2 plus 6 is 8, so our score is 8, and we roll it again. So we want to model, mathematically model, a series of random events and just add them all up. So the model would end up being, our score would be n, the number of times we roll the dice, times, and this is now a random event. So D is going to represent, what we'll have to do, maybe like on a computer, we could model, like have an event that spits out a number between 1 and 6, with each number having a 1/6 chance, and then do that n times, and then have a running total. And then maybe we could run that experiment over and over and over. But there's a randomness to it. It's not going to be an exact number because there's a random component to this event. So now if we did this model, we say we're going to take a discrete number n, the number of times a random event. This thing d represents the roll of a dice. We could ask some interesting questions like, what is the expected value of this? We don't know what this is going to be. What would be, like, just for example, the extremes? What would be the lowest number we could get? I guess if we had a 1 every time, let's say n was 10, we could get a score as low as 10, and the biggest score would be 60. And somewhere between there is what's more likely to happen, right? So, but some interesting questions we might ask for this model is, what is the expected value of the sum? What is the expected value of each increment? In other words, what is the expected value of d each time we roll it? How much will this vary with the variance? How much will this vary away from the expected value? And what would the variance of each roll be? What is the variance of d, and then what is the variance of the entire score? So variance comes into play, and expected value comes into play when there's a random event. Okay, so this is, okay, so this, let me go back to this model. This model, n times d, is kind of like the intuitive model we would just for rolling a dice n times. Now what we're going to do, I'm just going to walk through a set of making changes to this model that you might think are just, I'm making it more complicated, but hopefully in the end there'll be a reason for doing this. So let's, first of all, let's notice that every time you roll the dice, the average, the expected roll of the dice is going to be 3.5, right? 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6, the chance of each coming out, comes out to be 3.5. So let's model rolling a dice n times. Let's model it this way. Instead of just looking at the score from 0 to 6, let's give you 3.5 credits. Let's award you 3.5 points, credits, 3.5 points for each time you roll the dice, regardless of what the outcome is. But then when we look at the dice, the value, we're going to subtract the 3.5 points that we just gave you. Right, so you might think we're giving you 3.5 points, then we're taking it away. You might think, what's the point of this? But it's going to make our model, look bigger, but in the end, hopefully our model will be more interesting. So what we're going to do is this. We're going to say, the new model is, if you roll the dice n times, I'm going to give you 3.5 points for every time you roll the dice. Then, and this is new. This part is now new to our model. Our model used to be n times d, right? That used to be our model. Now I'm giving you 3.5 points every time you roll the dice. But then whatever score you got, I'm subtracting 3.5 points from it. So really, it's the same exact model. It just has more print and it looks more complicated. Okay, so it sounds strange and maybe even pointless, but this is a different way of modeling the same outcome, the same score. Okay, so maybe just now it's just some cosmetic difference. So now let's invent a new dice. Instead of the dice having 6 faces, and the faces being 1, 2, 3, 4, 5, and 6, let's make a new dice, and we'll put on their faces -2.5, -1.5, -0.5. Oh, this should be +1.5, +1.5, and +0.5. Sorry about that, but you get the idea. So this new dice with the star, so I'm now going to call this dice with 1 star. This is basically the dice that we're comfortable with, 1 through 6, but the score having 3.5 points subtracted off of each. So if you roll a 1, it's really like you rolled a -2.5. And if you roll a 4, it's really like you rolled a +0.5. Right? Okay. So this should be +0.5, and +1.5, and +2.5. Okay. So the new strange equivalent model now becomes this. You get 3.5 points every time you roll the dice, and then you get n times this new dice, which might be subtracting. It might be subtracting points from you, it might be adding extra points to you. So like for example, if you roll a 6 on the old system, here you get 3.5 plus 2.5, which is 6, right? So really nothing's new, it's just the model has changed. Okay. Okay, so let's now look at, here's our new model. Your score after n rolls is 3.5 times the number of rolls plus n times this new dice, which has minus faces and plus faces. Okay, so let's first look at this term, this first term. The 3.5 is discrete and contains no randomness. If you roll the dice 10 times, you get 35 points. You roll the dice 100 times, you get 350 points, right? Okay. Its value will be exactly 3.5 times n. So its expected value, if there's no randomness, its expected value is exactly 3.5 times n. And there's no variance, it won't vary. If you run this experiment with n is 10 today and run it again tomorrow, this is going to keep coming out 35, 35. There's no randomness to it at all. So it looks like we made, what we started off with is the rolling of the dice. We made it, looks like we made it complicated, but we actually have 2 terms now instead of 1, and we had to manufacture a different dice. But the 1 term kind of tells us right away, has a concrete component to it. That score is going to be 35 if, for example, we choose n as 10. The other thing interesting about the, let's talk about the second term. So the second term, this part, n times this new dice. Each roll of the new dice has an expected value of 0, right? Because we made it symmetrical. It was like plus a half, plus 1.5, plus 2.5, minus a half, minus 1.5, minus 2.5. So it's an interesting dice in that its expected value is 0, whereas the original dice, the dice we're used to, has an expected value of 3.5. This one has an expected value of 0. So with each roll of this new D star dice has an expected value of 0. If we rolled it n times, the expected value of n times that would still be 0. And now the variance, how much does it vary? You know, the variance from statistics is a statistic about how far away it is from the average. If we go and calculate the variance ends up being, if you remember this formula, it's each particular roll minus the expected value. The expected value is 0. So it would be like a half, it would be a 1/6 chance of it being 2.5, 1/6 chance of it being 1.5, 1/6 chance of it being a half, and then squaring that term, adding them up. And this ends up being 2.5 squared plus 1.5 squared plus a half squared plus a half squared plus 1.5 squared plus 1.5 squared. Add that all up, divided by its weight of 1/6, and we get a variance of 2.91. And if you take the square root of that, you get sigma, right, 1.7. So that just happens to be this random dice. So an interesting property about this dice is, number 1, its expected value is 0. Now, if we were going to write some computer software, and we were going to make like a collection of random events, it would be nice if, it would be very common to have a random event whose expected value is 0, and maybe its standard deviation is 1. That's sometimes called, in a normal distribution, that's called a standard normal. So if we had a toolbox, we had some a computer function that returned us one of those, well then all we'd have to do is multiply it by some factor to turn it into this. Maybe multiply it by a factor of 1.7, and then it would become this dice. So let's make one last change to this model, which started off very simple. We're rolling a dice many times. Now we're going to change this D star. I want to shrink the numbers down so that the sigma is exactly 1. And the only reason I want to do that is so that way we could ask a computer, give me a dice that has 6 faces on it, that has an expected value of 0 and a standard deviation of 1, and then I'll multiply it by something to turn it into like what I believe a dice is. So, we're going to change the D star dice, we're going to make a new dice, so that its sigma is exactly 1. So we're just going to take the D star dice that we had, multiplied by the reciprocal of 1.717, and it'll make the numbers get a little bit smaller. So now instead of it being negative 2.5, negative 1.5, negative 0.5, 0.5, 1.5, and 2.5, the numbers became 58, 59% of what they used to be. So now try to imagine a dice that has 6 faces on it. One says minus 1.465, whatever. One face says minus 8787, one face says minus 2929. Another face says 292.2929, 0.8787, and one face says 1.4653. And imagine we're rolling that dice. This is now a dice that has, this D star star is a dice that has an expected value of 0 and a standard deviation of 1. So that was kind of our whole, in the end that was our goal, to make that dice. And now all we'd have to do is take that result, multiply it by 1.7, and now we have the D star dice. And then if we add 3.5 for every roll, we have the original, what a real world dice is. So all we've done is just played around with the model to come up with this model. So this is actually remodeling an original rolling of a dice n times. It's just a very strange, you might say, what was the point of this? But this is, what is our score after n rolls is 3.5 times the number of rolls plus the number of rolls. We're going to multiply that by a dice that, based on its faces, the values on its faces, has an expected value of 0 and a standard deviation of exactly 1. Then we're going to multiply it by this factor 1.717 to make it become like a dice like we know. So this model plus the original one, Sn equals n times an original dice, nd, is the same model. It'll give the same exact results. But if we make one of these in our toolbox, then we could use that for many, many different models, not just dice. We could use it for anything that needs, well actually, it's not going to come up too often. It would be anything that needs a 6-sided random event where the gap between each of the 6 events are exactly the same. We could use this to model that. The only thing I can think of in the world that has a 6-sided event is a dice, right? But anyway, what we're going to do in financial mathematics is, instead of it being a 6-sided dice, it's going to end up almost always being a random, a normal event with a mean of 0 and a standard deviation of 1. That's the event we're going to keep asking the computer for, and then we're just going to use factors here to expand and contract how variable it is, what its variance is, or what its volatility is. So we're going to see, our model is going to follow this form a lot in financial mathematics. We're going to have some score, and it'll mostly be an S for stock price, but it could be really any price. And it's going to have a component, it's going to have a component here, which lets us know kind of how much we expect it to go upward. As long as this is a positive number, it's going to expect it to go upward as n goes upward. And then there's going to be a term that has an expected value of 0, and as long as we keep adding this, it's not expected to make our score go up or down, it's expected to make our score vary. So this term, let's see what we have here. Notice that D star has an expected value of 0 and sigma of 1. This term, therefore, has an expected value of 0. The term 3.5n is therefore the expected value. So this contributes nothing to the expected value. This term actually contributes just to how much it varies. This term is the only term that tells us anything about the expected value, because whatever the expected value of this is will be unaffected by this. This has an expected value of 0. So for example, if I said to you n was 10, and I asked you for this model, if I said n was 10, and I asked you what is the expected value, you could immediately know, ignore this part. This part doesn't contribute to the expected value. That would just be 35. Whereas with rolling a dice 10 times, the model that said n times d, where d is possibly a 1, possibly a 2, if I said what's the expected value, you'd have to figure out what's the expected value of a dice and then multiply that by 10. Okay. So, so this factor in front of this random variable is going to be a magnitude of how much this event, which has an expected value of 0 and a sigma of 1, how much to amplify that by. So this term will typically be referred to as the drift term, meaning if you started at a certain number, you start drifting, and if it's positive, you'll start drifting upward. If it's a negative number, you'll start drifting downward. This term will tell you how volatile you are. So you might be going upward, but not moving too much, or you might be going upward and moving a lot, but heading upward, if this coefficient in front here is large. Okay, yeah, so once again, this is the drift term, and maybe this would be, what would be the best word for that? The volatility term? Yeah, yeah, I guess we'll typically use the term volatility, how volatile it is, but it means how much it's moving away from the average. So, so like I say, what we're going to do almost always in our modeling is we're going to have, so just for example, we'll go over examples in financial mathematics a little bit later on, but what would you expect for a well, let's say one example. Let's say you had a bank account. You're putting money in the bank, and it's expected to go up at 5% over the course of a year. And let's say it's some crazy world where, like, the bank will never go out of business, and you'll definitely get your 5% for sure. What would the equation look like for modeling your bank account? Well, it'd be a 1.05 constant times the amount in your account, and it won't vary at all. So this term will be 0. There'll be no variance to it. But let's say you bought some stock, and the stock was expected to go up 5%, but it may go down, it may go way up, but for some reason you believe it's expected to go up at 5%. Then you might expect to see something like the model for that stock might be like 1.05 times the price of the stock plus then some number that represents the kind of the randomness or wildness of the stock times the price of the stock. So maybe if it's a stock like Google, which has a habit of going up and down a lot, you might expect to see a high number here. But if it's a stock like Coca-Cola, which doesn't go up and down too much because people are thirsty and they don't get a lot more thirsty or less thirsty, you might expect to see a very low number here. And what we'll end up doing is not using this D star star for a dice, but we'll end up using a random, normally distributed variable with a expected value of 0 and a variance of 1. And just multiply it. So what we could then do is we could kind of take the mathematical model for a Coca-Cola stock and a mathematical model for, let's say, Google, and compare the two. And we could see, you know, a ratio of how much one is more volatile than the other. As long as we keep putting our stock equations in this format, then with our eyes we can go, oh, here's how much it's expected to go up, here's how much it's expected to be volatile. So that'll be the model we'll be following in our financial applications. Okay. Any questions about that?
No, I think I got what you were trying to get to at the end of the model. So you changed the original model from where it was to give us, basically use it in terms of stock and finance.
Right, so really what I was doing was I was taking something that we understand well, like rolling a dice,
Correct.
and then I was trying to flip it around so there would be two parts to it. One part that is just showing us how much we expect to go up,
Uh-huh.
and another part that captures the randomness to it.
Correct.
But then I also wanted to do, because I know what we're gonna be doing is, I wanted to have the random part have the property that its expected value is 0 and its standard deviation is 1, because we're gonna be doing something just like that. We're gonna remove this D star star and we're gonna put in, what they call a Wiener process, but it's basically an event that we just keep randomly generating, and its property is it's normally distributed, not like a dice, which would be discretely distributed, would be what, uniformly distributed, but it would be normally distributed, so it has the bell curve to it, and its average is 0 and its standard deviation is 1, and then we're just going to amplify that by a constant in front of it. And yeah, once we're comfortable with that, you're going to see like a lot of our equations, and this will be for stocks, options, everything is going to have an equation laid out like this. And this is going to have a discrete component to it, where we could use regular mathematics. And this part, because there's a randomness to it, we can't use it like regular mathematics, like do integrations on that. We have to use a different type of mathematics on it. Because it's not fixed. There's a random component to it. Okay, good.